So the first part of our lesson today is going to review a geometry topic of special right triangles. And then we're going to look at how it connects to that circle that we built last time in order to finally build up some of this trig information that we want to be able to recognize very quickly. So a small reminder that in geometry, you guys learned special right triangles, and they were either 30, 60, 90s or 45, 45, 90s. That's why we only marked 45-degree angles, 30-degree angles, and 60-degree angles on our unit circle, because these angles are special. They're used a lot more often in math, so we don't need to know everything on our own, but these ones come up often enough where it could be important. So in geometry, you guys actually found a pattern of how these worked. And in a 30, 60, 90 triangle, remember that the hypotenuse is always across from the 90. And then in a triangle, shorter legs are across from shorter angles and longer legs across from longer angles. So in this triangle, the short leg would be across from the 30, and some sort of like middle length thing, something between the short leg and the hypotenuse, would be across from the 60. And you guys found a pattern for them. I'm going to use N to represent the pattern. If you knew the number that was the short leg, you knew that you could get the other leg by taking that number and timesing it by the square root of 3. Or you could find the hypotenuse by doubling the short leg. In other words, timesing the short leg by 2. So some examples here of how this works. And there are some that you guys will figure out really quick, and some will take a little longer. So I'm going to focus first just on 30, 60, 90s. And your homework tonight will have you give you triangle drawings, and you'll have to find missing pieces of them. So I'm just going to set up a 30, 60, 90 and remind myself of that pattern that we just talked about. And then I'm just going to do each problem separately with you guys. So each of these rows in this table is a problem. So like problem 1 right here, they're giving us the middle length leg. So I know the side across from the 60 is 5 rad 3. Now, most of you guys like it when this has a rad 3 right here because it matches the other one, and it's really easy to see that the n is 5. But it won't always have a rad 3 there. Sometimes when you times something by the square root of 3, it might work out to just be a regular number if it already had a radical inside of it. So just a little reminder, if you have to, you can always use the given piece to set up a little equation. I know that 5 rad 3 is supposed to be my n rad 3 in this equation. So what is n? So I divide both sides by rad 3 to get n by itself, and I see that n is 5. That means in this pattern, the n should be 5. In other words, the short leg works out to be 5, and the hypotenuse would be 2 times 5, which works out to be 10. Okay. I'm going to try this again with the next piece of information. So same diagram, because this is all about 30, 60, 90s. If I look at this second row, it tells me that the short leg is 11. That's my given piece of information. So in this one, I don't really need to solve it because they're giving me the one piece that's just n by itself. The value of n in this pattern is 11. That means to find the middle length, I use 11 for n and I times it by rad 3. And so without a calculator, we just get that that middle length leg is 11 rad 3. And for the hypotenuse, I would do 2 times 11, which gives me 22. All right, now I'm going to do a different situation. Start over and do the third one. In the third one, they give us that the hypotenuse is 8. So I know that the hypotenuse is 8. In other words, 2 times something made 8. So again, a little equation is helpful. 2n turns out to be 8. What is the mystery value of n? That would be 4. So I want to use 4 for the short leg, and then plug 4 in for n to find the middle length leg. So this information tells me that the short leg works out to be 4. The middle length leg is 4 times the square root of 3. All right, the next example gives us the short leg of 9 in this fourth problem here. Again, that's kind of the one that's the nicest. If they tell you that, you can just plug 9 in. Actually, let's make this a little harder because feel like that's a little too easy for you guys. Let's make this 9 rad 3. Well, that'll rattle your brains a little bit just to make it so when you get to the worksheet, you can do the problems. So let's say they're telling you the short leg is 9 rad 3. That means the n is 9 rad 3. So when you go to find the long leg, the n part is 9 rad 3, and that's being multiplied by another rad 3, and then you have to finish that multiplication. So rad 3 times rad 3 is rad 9, and you know rad 9, the square root of 9 is 3, and 9 times 3 would be 27. For the hypotenuse, you would be doing 2 times 9 rad 3. You can multiply together the 2 and the 9, and that would give you 18 rad 3. So if they gave you a more complicated short leg like 9 rad 3, we found a middle length leg of 27 and then a hypotenuse of 18 rad 3. And then our final situation for these types of triangles, in this case, they're giving us the hypotenuse of 1. So if the hypotenuse is 1, in other words, 1 is equal to the 2n part of the pattern, go ahead and find n. So cancel out whatever's with n, and we get that n is 1/2. That means the short leg is 1/2. The middle part is going to be 1/2 times rad 3. Remember, we just multiply fractions across the top and the bottom. So 1 times rad 3 is rad 3, and 2 times 1 is 2. And so this middle length leg would be rad 3 over 2. All right, now we're going to move on, and we're going to look at the 45, 45, 90. Before we do that, let's identify and remind ourselves what we found out in geometry about that. In a 45, 45, 90, the two smaller angles are equal. Then you have your 90, and you know that across from the 90 you have the hypotenuse, and that means that both of these legs, one is not shorter than the other, they are just both the same. So our pattern for these was that the leg values were the same, and to find the hypotenuse, you multiplied that leg value times the square root of 2. So that was the pattern we used for 45, 45, 90 triangles. So this second chart is all about 45, 45, 90. So again, this is like 5 different problems where we know we're looking at a 45, 45, 90. And then we're going to go ahead and use the given information to see if we can figure out everything else. So first one, we have a leg length of 4. But again, both the legs are the same. So once we know one of these is 4, we automatically know the other is 4 as well. And then to find the hypotenuse, if you know the leg, you have the n value. So it's just that value times the square root of 2. So the hypotenuse is 4 rad 2. If we did the same thing where one leg was 11, you can see the pattern that we would end up with these same values. Now in the third problem, they're giving us a hypotenuse value of 13 rad 2. So you know that 13 rad 2 and n rad 2 are the same. So again, a little equation can help you. 13 rad 2 is equal to the part of the pattern that is n times rad 2. If you want to know what n is, just divide both sides of this little equation by rad 2. And you can see that the n value being used is 13. So that means that each of the legs are 13. For the fourth example, again, let's make this more difficult. Let's go ahead and give ourselves a rad 2 here so you guys can see what it feels like when it's not in the spot that you want it to be in. So here they're telling you the leg length is 9 rad 2. So the leg is 9 rad 2. That tells you the n and automatically the other leg. So this is also 9 rad 2. So how do you find the hypotenuse? The hypotenuse is the n value, which was given to you as 9 rad 2, but it has to be multiplied by rad 2. So you have to multiply these together. You have a 9 on the outside. Rad 2 times rad 2 makes rad 4, and you actually know that radical. The square root of 4 is 2, and 9 times 2 will give you 18. All right, and then for our fifth and final, we're going to look at this last one where they say the hypotenuse is equal to 1. So again, a little equation will help us. The thing that's n rad 2 is supposed to work out to be 1. So what does it mean if n rad 2 is equal to 1? If I divide by the rad 2 to get n by itself, it means that n is equal to 1 over rad 2. And if you guys remember, we generally don't leave radicals in the denominator of a fraction. So we multiply by rad 2 because the square root of 2 times the square root of 2 gives us the square root of 4, which is just 2. That's how we're getting rid of that radical there. But then we also have to multiply the numerator and we get this. So we get this expression. That's our n value, the square root of 2 over 2, or the square root of 2 divided by 2. And so that's each of these. And we don't have to do anything to those. Those are the leg values. So each leg here then is square root of 2 over 2. So this is what most of your homework is going to be about, doing these calculations. And then we want to finish the notes today by making a small connection or a big connection to our unit circle. So when we look at our unit circle, I first want to point out to you that it doesn't matter how big this is. So we're not going to do all these problems. This chart is really big, but I just wanted to show you guys something. So I'm going to focus on this first row for a second. These are the lengths that we got from doing one of our problems. There is a 30, 60, 90 triangle. And if the short leg was 2, then you figured out these other leg lengths, okay? Now I want you to look here at these calculations. Let's say you wanted to calculate the sine of 30. Remember, if we're looking at 30, 2 is the opposite, and 2 rad 3 is the adjacent, and sine is opposite over hypotenuse. So it would be 2 over 4, which reduces to be 1/2. Now let's say I had a totally different triangle. I'm just going to pick a different one in the list further on, okay? It's also a 30, 60, 90 triangle, but it's bigger. See its side lengths? The angles are the same, but it's built with bigger sides. The small side is 8, which means the other side's 8 rad 3, and the hypotenuse is 16. In this triangle, if you find the sine of 30, 8 is the opposite, 8 rad 3 is the adjacent, and 16 is the hypotenuse. You would get opposite over hypotenuse is 8 over 16, which also reduces to 1/2. So basically this means even if the triangles get bigger, the calculation for sine of 30 stays the same. So you know what the answer is going to be to all of these? It doesn't matter how big the triangle is, we're always going to get 1/2. All right, let's use these two examples to see if we see the same pattern happening for cosine of 30. So cosine is adjacent over hypotenuse. So in this case, that would be 2 rad 3 over 4. That reduces to rad 3 over 2. In the bigger triangle down here, it would be 8 rad 3 over 16. The 8 and the 16 reduce, and that also reduces to rad 3 over 2. So it turns out that no matter how big your triangle gets, you always get the same answer for cosine of 30. And that's going to be rad 3 over 2. Now let's look at the tangent of 30. Tangent is opposite over adjacent. So I'm going to write that off over here. It's 2 over 2 rad 3. The 2's will cancel. And that gives us 1 over rad 3. And like we talked about last time, we can't keep that radical in the denominator. So when I adjust that, I get rad 3 over 3. When I do this same calculation for the other bigger triangle, and I do opposite over adjacent, it would be 8 over 8 rad 3. Again, the 8's would cancel, leaving me with the same answer as before. So again, I get the same answer for tangent no matter how big the triangle is. The tangent of 30 is always equal to rad 3 over 3. So my point in showing you this is that it doesn't matter how large the triangle is. We're going to get the same answers for sine, cosine, and tangent. The same thing would happen if we changed it to 60 degrees or if we were using 45s, which we'll look at in a minute. So what does that mean? That means that if somebody wants to memorize or know about their trig functions, they can choose whatever size triangle to use and get the answer. So mathematicians chose what they think is the best triangle. That's why they chose the unit circle, so that the radius is 1 unit. Okay? You guys already solved a 30, 60, 90 triangle when the hypotenuse of the triangle is 1. I'm going to look back right here. So see these measurements right here? They said if you had a 30, 60, 90 and the hypotenuse was 1, that these were the lengths of the leg. 1/2 was the small and rad 3 over 2 was the other length. So if I draw that triangle in my unit circle like I do right here to mark a 60-degree angle, then that means if this is set to 1 as the hypotenuse, I know that the short leg is 1/2 and the other leg is rad 3 over 2. The reason that's important is because that tells me that these coordinates right here then are 1/2 rad 3 over 2. And that gives me some more information for my unit circle. This is the same triangle, but it's laid down a different way because we only wanted a 30-degree angle right here. So the short side is over here and the middle length leg's over here. And that tells me at the position of 30 degrees for this point, the x coordinate is rad 3 over 2 because that's how long we go horizontally. And the y coordinate is 1/2 because that's how high we go vertically. We can do the same thing for a 45. I'm not going to make you guys do the chart. Again, the point is that no matter how big the 45-degree angle is, they all work out to be the same measurement for the sine, the same measurement for the cosine, and the same measurement for the tangent. So if we make it whatever size we want, and again, mathematicians believe that the best size to make it is to make that circle have a radius of 1. Then if we mark a 45-degree angle on our circle with a radius of 1, how long are these distances of the triangle? Look back at our calculations. We did this today right here. In a 45, 45, 90, when the hypotenuse was 1, these were the lengths of the legs, rad 2 over 2, and they're both the same. So in a 45, 45, 90, when that's 1, these are rad 2 over 2. And again, why is that important? Because that means now not only do I know that this mark on this circle marks a 45-degree angle, but I could also tell you that based on the x and y axis, what numbers belong in the coordinates. So now we're going to take those coordinates and we're going to fill them in to our unit circle. Okay, so go back to the unit circle that you guys had yesterday. We marked all the special angles on it. It looked like this. And so just to give you guys a picture, you guys don't have to draw all these markings in on your circle. I just want you to see it as I go through it. When we mark a 30-degree angle right here, we know this angle's 30. If you connected it back to the axis, you're building a right triangle that's a 30, 60, 90. And again, this is your unit circle. That means the radius is equal to 1. Mathematicians were allowed to pick that number since the calculations always worked out the same. They picked 1. We know if the hypotenuse is 1, what the other lengths are on the triangle. In this case, this one would be 1/2 vertically, and horizontally would be rad 3 over 2. Those numbers are the same numbers that make your x and y coordinate. Your x coordinate is how far you went horizontally, which is rad 3 over 2, and your y coordinate is how far we went vertically, which is 1/2. Once we have those markings for one of our 30-degree angles, we should be able to find the others because this angle over here is also 30 degrees away from the x-axis and builds the same triangle. The only difference is it somehow got over here in quadrant 2. So remember, this is quadrant 1, this is quadrant 2, down here is quadrant 3, and on the other side quadrant 4. How do you land in quadrant 2 if you're building the same triangle? The only difference is you would make the x-coordinate negative. So it's the same distances because it's the same size, but because it landed on this portion of our coordinate plane, the x had to be negative. And then we can use that same information to figure out all of the 30s. So down here in the third quadrant, how do you get to this position? It's the same size as all the other 30-degree triangles, but you had to go to the left on the x-axis and then down in the y-coordinate, so you have to have both of these numbers be negative. And then lastly, over here in the fourth quadrant, to get there, you go to the right and then down, so it's a positive x-coordinate, but a negative y-coordinate. And now we can do the same thing with the 60s. So if we looked at it right here at the 60, and again, you don't have to draw this whole triangle. I'm going to draw it once to give you perspective. That means this is the 60-degree angle, and you know the hypotenuse is 1. Now the short side's over here for the x. It's 1/2. And the longer side, or the middle length leg, is now the y-coordinate of rad 3 over 2. So the coordinates to land on this point right here would be to go horizontally 1/2 and then up rad 3 over 2. I know it looks really similar to the 30s. That's because the 30 and the 60 come from the same triangle. So they do have similar numbers there. And again, once we find one of those, we can find the others by just thinking about those same distances, but to land in a different quadrant, like the second quadrant over here at 120, we would have to have a negative x and then a positive y. And to land down here in the third quadrant at 240, you'd have to have a negative x and a negative y. And then to land over here at 300, which is also 60 degrees, you have a positive x and a negative y. So then we want to look at our 45s. So again, same idea. You guys don't have to draw the triangle, but just to give you a perspective, we're trying to figure out the coordinates by thinking about this. If we know this angle is 45 degrees and we picked a hypotenuse of 1, you guys already did the calculations. The legs of the triangle are the same and they come out to be rad 2 over 2. So the x distance is rad 2 over 2 to land at this point, and the y distance is also rad 2 over 2. And again, we can do the same thing with all the 45-degree angles in this diagram. To land at 135 over here in the second quadrant, it's the same distances as the 45. The triangle's the same size, but you have to have a negative x to get over here and a positive y. To land at 225 in the third quadrant, you need a negative x as well as a negative y. And then to land at 315 in the fourth quadrant, you need a positive x and a negative y. So that leaves the only things that don't have coordinates are along our axis, like right here. But remember, we just said we are choosing that this circle is going to have a radius of 1. That means you know this distance is 1. So right here at 0 or at 360, your x is 1 and your y is 0. If you want to land up here at 90 degrees, you have a 0x but a 1y. If you want to land over here at 180 degrees, you have to have a negative 1x and a 0y. And if you want to land down here at 270 degrees, a 0x and a negative 1 for y. So leave those in your notes for now, and then we'll figure out how all of that is going to help us quickly calculate sines, cosines, and tangents of our special angles.